So we want to do an example of calculating a surface integral of a vector field. The formulas sometimes make it look more mysterious and intimidating than it really is. Let's do a simple example. So here's our surface. Our surface is going to be the following. It's going to be a cylinder sitting on the xy plane. So here's the bottom of the cylinder sitting on the xy plane, and the top is going to be up here somewhere. And this is dotted because it's behind, and in fact this is not because we can see it. So this is our surface. Remember, we're dealing with a surface, not a solid. So our surface is just the can, including its two caps. Okay, the top, the bottom, and the sides. Okay, this is the surface. It can be expressed as, so S is, let's write all the x, y's, and z's such that, or I'll just save the time. S is x squared plus y squared equals 4. That's going to be S is, wow, I'm messing it up. S is the cylinder x squared plus y squared equals 4. Remember that when we write that, there's no z's here, but in 3 dimensions it's a cylinder, right? It's all the points that satisfy this, independent of what z is. Okay, so this is going to be 2, and this is going to be 2 on the y-axis. Where z's are between 0 and 3. So this is going to be 3 on the z-axis, including the top and bottom. Okay, including the two caps. And what we want to calculate, so this is S. Is it clear what S is? There's going to be a field. So F of x, y, z is going to be a vector field. It's going to have 3 components, and it's not going to be a too complicated one. So it's going to be 4x in the I direction minus 2y squared in the j direction plus z squared in the k direction. So this is P, this is Q, and this is R. Note that in this simple example, P only has x's in it, Q only has y's in it, and R only has z's in it. But in general, they all have all 3 variables, right? This is a very simple example. So this is the field, and we want to find the flux of F through S. But there's still one more thing we have to say in order to make this well defined. We have to say if we want the outgoing flux or the ingoing flux. That's changing the directions of the normal on the surface, and that changes it by a minus sign. Okay? So we're going to find the flux of F through S, and let's add find the outgoing. Okay? So the normal on S is going to be, on the top, the normal is going to be pointing in this direction. On the bottom, the normal is going to be pointing in this direction. And on the sides, the normal is going to be pointing in this direction. Clear? And the way we're going to do it, we're going to break S into 3 surfaces. The side, which is just the cylinder. The top and the bottom, which are just 2 disks. And calculate the surface integral of the vector field on each one separately, and add them up. Okay? It's an obvious thing to do because the surface is comprised of three different surfaces. We can't parameterize the entire thing at once. Okay? So we're going to call this top part, we're going to call it S1. The bottom part, we're going to call S2. And the sides, we're going to call S3. And S is S1 union S2 union S3. Good? So now let's start calculating the surface integrals. Let's start with S1. So what is S1? So S1, the easiest way to do, not the only way, one way to do it, and an easy way to do it, is to note that S1 is the graph of a function. Do you agree? What function? The constant function f of xy equals 3. Do you see that? So let's write that. S1 is the graph, or part of the graph, of f of x of z equals 3. F of xy equals 3. Do you agree? Here's S1. Sitting up here at 3. Do you agree? So let's write z equals f of xy, little f, which we just invented, which is the constant function 3. Does everybody see that? Okay. So a parameterization of S1, we can parameterize S1 as r of xy equals x, y, f of xy, which is just 3. Do you agree that this is a parameterization of S1? All the points on S1 are of the form x, y, 3, where xy belong to the circle down here. Those are where the xy's live. To d, and d in this case is x squared plus y squared is less than or equal to 4. Do you agree that this is a parameterization of S1? Good? Now what's the normal, right? What's the normal? We have to take, remember, let's go a couple of boards back, or we're actually going back in time to the previous clip. I just left it on the board. What we want to calculate is the double integral of the field dot the normal over the domain of the parameters, right? This is the surface integral of a vector field. Double integral over the domain of the parameters of the field dot the normal. Do you agree? Good? So what's the field? The field is this, PQR, 4x minus 2y squared z squared, right? The normal we'll calculate in a minute. We have to dot them and then calculate everything on that parameterization, which is a very easy parameterization to work with. Okay? So what is the normal? The normal, do you remember what the normal is when the parameterization is using the fact that it's a graph of a function? We discussed it a couple of clips ago. The normal is minus fx minus fy 1. Remember that? So in this case, what is the normal? What's f? F is just the constant function 3. So its derivatives are what? Zeros. So the normal is just 0, 0, 1. Do you agree? That, of course, fits the picture. The normal is just pointing in the direction of the z-axis. It's k. K itself. Do you agree? Does everybody see that? Good? So what we need to calculate is the double, so the flux, so the double integral over S1 of f dot ds is just the double integral over the domain. The domain is in this case is just the disk in the xy plane of the field. The field was the p component was 4 times x. That was the I component, the p component of the field. So I'm going to write here, sorry, 4x. The q component was minus 2y squared. So I'm going to write here minus 2y squared. The r component was z squared, but what is z here? It's 3. We're working on this parametrization. So z squared is 9. This is f evaluated on this surface. Do you agree? Dot 0, 0, 1. F dot n, and then u and v were just x and y, so this is the integral we have to calculate. Clear? Now dotting these two vectors is really fun. You just get 9, right? So this is 9 times, well, let's stick to standard 9s. 9 times the double integral over this disk, dx dy. What's the double integral of the function 1 over a domain? Just the area of the domain. The domain is a circle in the xy plane of radius 2, right? So what's its area? 4 pi, right? R squared times pi. So it's 4 pi times 9, so we just get 36 pi. Do you agree? So this is the contribution to the flux of the surface S1, which is the top. Okay? What is the contribution of the bottom? What's good? Let's do S2. S2 we're going to do in blue. S2 lives down here. This is S2. Do you agree? Let's parameterize it. What's the parametrization of... Do you agree that S2 is also part of a graph of a function? Which function? Right, just a 0 function. Do you agree? So the parametrization of this is going to be x, y, 0. Right? And everything is going to be exactly the same, except here, instead of this 9, we're going to have a 0. And one more thing, the normal we chose pointing downwards. Okay? So for S2, dead blue, for S2 is the graph of z equals fxy equals 0. The normal was pointing this way, so this is going to be 0. And everything is the same. Everything is the same, except here we're going to have 0, and here we're going to have minus 1. Okay? Why don't we see it here? Because when we calculate the normal, we don't get its direction. We have to choose it, right? And we chose it here to point downwards. So it's going to be not 0, 0, 1, but minus that. 0, 0, minus 1. Okay? And now what's going to be the contribution of S2? It's just going to be 0, right? This specific field does not have flux through S2. Okay? The reason is that the field, and you can ask, how could it be? How could the field not have flux through S2? But that's exactly clear when you think of the net that you put in the water. The field is 4x minus 2y squared plus z squared. Those are the components, right? And when you look at the xy plane, sitting like this, the only contribution of the field, since the normal is pointing this way or this way, the only contribution is the z component of the field, right? That's the only component of the field that contributes to the flux. But at z equals 0, it doesn't have a z component, so the field on the xy plane is actually pointing parallel to the surface, so it doesn't contribute to the flux. Clear? If you were to draw these little arrows down on the xy plane, they would all be sitting like this. They won't have a z component, therefore they won't contribute to the flux. Is that clear? Good? Okay, so are we done? Not exactly, right? We still need to do the cylinder itself, what we called S3. So let's do that. So I'm going to erase all this. Are there any questions on this? Everybody good? So I'm going to erase this. All we need to remember is that S1 and S2, well, let's add here 0 and 0. And S1 and S2 contributed together 36 pi. Okay, let's see what S3 contributed. Okay, this is going to take different arguments. It's no longer the graph of a function. We're going to have to parameterize it differently. And of course, the parameterization that first comes to mind is using cylindrical coordinates sort of parametrization. So for S3, S3 is the cylinder part, is this thing. Okay, it's the sides, This is S3. So what do we have? We need to parameterize it. So what would be the parametrization? So the parametrization would be R of UV equals, based on cylindrical coordinates. So the radius is fixed, it's 2, right? All the points have rho equal to 2, and then it's going to be 2 cosine, did I call it theta or phi? I called it phi. 2 cosine phi, so I can't call it R of UV, duh. R of phi and z. So in general, it's rho phi in z, but rho is fixed. It's just 2. So it's 2 cosine phi, 2 sine phi, and z. This is the parametrization. Okay? Where z, where phi ranges between 0 and 2 pi, and z ranges between 0 and 3. You should be able to see that points of this form, points x, y, z of this form, where phi and z are restricted. I'm sorry for calling it phi and not theta. That's how it's written in my notes, and if I change it, I might get confused. So instead of me getting confused, I'd rather confuse you, right? Huh. Sorry. So you should be able to see that points satisfying this, points x, y, z satisfying this, are precisely the points on the cylinder between 0 and 3, and only those. Okay, it's a parametrization of the cylinder. Okay, so let's see what we get for, remember what we need to calculate. We need to calculate f dot n and then plug that into the double integral, okay, over this domain. So what is f dot n? It's going to be the determinant PQR, but let's add another. It's F dot R phi cross R z. Those are the components of the normal. And now we're going to write this triple product. So the top row has to be the components of F, right? P, Q, and R, evaluated on the surface. So P was 4x. That was the P of this field that we're dealing with. So P was 4x. X is 2 cosine phi. So I have here 8 cosine phi. This is P evaluated on the surface, on the parametrization. Is it clear what just appeared here? Q was minus 2y squared, evaluated on the parametrization. This is why 2y squared, or minus 2y squared, is minus 2 times 4, minus 8 sine squared of phi. And r was z squared. Z is just Z, so we have here Z squared in this parameterization. Is it clear what just appeared here on the board? Okay? Now, what are the derivatives of R with respect to phi and Z? So with respect to phi, I have here minus 2 sine phi, 2 cosine phi, and 0. And the derivatives with respect to Z are 0, 0, and 1. Do you agree? Good? This should be a function in phis and z's, in the parameters, in u and v in general. Everybody with me? Good? Okay. So this determinant, all we have left is 1 times this thing. So what we get is 16 cosine squared of phi minus, that makes it a minus, 16 sine cubed of phi. This is f dot n, evaluated on the parametrization. Good? Therefore, the integral over the cylinder S3 of f dot ds equals the integral, the double integral over the domain of the parameters, and I'm right away going to write it as iterated from 0 to 2 pi d phi of the integral from 0 to 3 dz of f dot n, which is this, 16 cosine squared of phi minus 16 sine cubed of phi. And this is what you need to calculate. Good? The z snake just contributes a 3, right? And then you need to calculate this, and it's again trig functions, and you need to find the antiderivatives. So I'm going to put a dot, and tell you what you get, and you can fill in the details on your own. You're going to get 48 pi. Good? So finally, the bottom line is the integral of f dot ds over S, over the entire surface, cylinder with the 2 caps, is 36 pi, which is the integral over S1, plus 0 plus 48 pi. Those are the contributions of the top, the bottom, and the sides. And the total is, what? 84 pi. Clear? Everybody good? Okay. So just a remark, along the way we said something that is useful for other examples. So this was an example, but along the way, note that we mentioned what happens when our parametrization is in terms of the graph of a function. Okay, that's an easy case, and then we know the normal right away. It's minus fx minus fy 1, right? And then you can use that. Okay, questions on this example? We'll of course do more, but questions on this one for this clip. Everybody good? Okay, wonderful. Okay.